Physics. I'm Mr. McConnelly, and today we're going to talk about electric potential. Now, you have heard of this before, but it hasn't been referred to as electric potential. You've heard of it as volts. Like when you pick up a battery, some batteries are labeled 1.5 volts, some batteries are labeled 9 volts, some are 12 volt batteries. And you're used to that, and you kind of think in your mind, okay, the one with the bigger volts has got more power or something. So you kind of have this idea of batteries. Well, the correct term for it is potential. And I'm going to kind of teach you what potential is, and then you'll have a better understanding of how potential, or as you call it, voltage, works. So if you look at my picture I have drawn here, I have a large positive charge located right here. And then at point A, I have a small positive test charge, and at point B, I have a small positive test charge. These two test charges are the same value. This is a larger positive value. Okay, fine. And you can see that A is closer. So, since they're both positives, what's the reaction? Is it going to be an attractive or a repulsive reaction between these two? If you're ignoring B for a minute. Repulsive, definitely. So A is going to get pushed away. And then if you ignore A for a minute and just look at B, well, B will also be repulsive or get pushed away. But when you're comparing the two, you got to think of them separately, but when you're comparing the two, wouldn't you think that A would get pushed away more strongly than B? Because A is closer. So you're already really close, and those two really don't want to be that close. So this one's going to really get pushed away fast or powerfully, and this one's going to get pushed away less powerfully. And the idea here, the concept here, is that we call this location. Now it's a relative comparison here because I haven't put any numbers, but this is a higher potential. And this is a lower potential. Just a comparison, higher, lower potential. Potential, though, is kind of an incomplete way to say it. Let me complete the sentence. If you were starting here at point B, and you were trying to move a positive to A, so if you're trying to move from low potential to high potential, it would require work. Back to an old term, work. A force over a distance. So if you move from here to here, it's going to require work. You're going to have to fight against the force of the electric field. The electric field is trying to push that thing away, and you're going to have to do work against it. So when we say potential, it's really potential fighting against the work, and there's an equation that ties this concept together. The equation can be found in your reference tables. It's V equals W over Q. And let me explain how that relates to this. Well, Q is the charge, just as we've learned about with coulombs of charge, but it's still charge is in coulombs. Okay? Again, I apologize for the Q. W is work. And that's the work it takes to move the positive against its will, or towards another positive. And work is in joules. And this new letter here is a V, not to be confused with velocity. Totally different topic. This is a V and it means potential. And potential is measured in units of volts, which is abbreviated of V also. Now that's confusing, but the other way you could write the units is joules per coulomb, which would be perfectly correct on a Regents exam. So, just to kind of summarize this quick again. You're taking a charge and you're doing work by moving it against its will, and that is the definition of potential. And potential is actually measured in volts. So when all your life when you've been saying, well, that's a 9-volt battery, what you're really saying is that has a potential potential of 9 volts, or has a potential of 9 joules per coulomb. Okay, so you're talking about its ability to move charges. Now, with batteries, you're always trying to take electrons and you're trying to push them into some device. Let's say these batteries are powering your phone. Okay, so you have batteries in your phone. Those batteries in your phone, 3.7 volts or whatever they are, they're trying to push the electrons through your phone, so they're doing work on them, and then that allows your device to operate correctly. Okay? So can you kind of see how potential works? Well, the next picture I'm going to draw you, just to solidify this completely in your mind, I'm going to give you 2 examples of large potential. And I'm going to give you 2 examples of small potential. Now remember, this is the potential to do work. So, large potential. If you had a negative here and a positive here, and they were far apart. Now I know that's vague, but this is all a relative scale. Okay? So if those 2 are far apart, you can see that they're going to be attracted to each other, and they have such a long distance to act upon one another. They're going to start pulling, and as they get closer, they're going to pick up more and more speed, boom, until they are attracted to each other. That's a large potential. In comparison, if I take the exact same scenario, a negative and a positive, and I put them close together, yeah, they're attracted, but they're only attracted for a very short time, and then they've already arrived at each other, so they're defined as a small potential. They have a small potential to do work. Now, the other example would be a large potential is if you take 2 like charges, 2 positives we'll say. Now those 2 positives are definitely going to be repelled from one another, and you put them very close. If you put 2 positives very close together, now they have a large potential because they're going to keep pushing and pushing and pushing for a long time, and they're going to push each other apart, and there's going to be a lot of work done. The opposite of that is if you put 2 positives and they are far apart to begin with. Yeah, they're going to push apart, but the interaction, since they're already far apart, is going to be pretty weak, and it's going to be what we'll say is a small or low potential. So those are some examples to help you visualize high and low potential. And if you talk about let's take a AA battery. A AA battery is a small battery, and it has 1.5 volts. And then you can get a big battery, like a D battery, and you know what the voltage is on those? 1.5. It's the same voltage. So there must be something else that's going to come into play here, because a D battery and a AA battery have the same potential. However, they don't react the same under circumstances when you're using them. So we're going to come back to, probably tomorrow or the next day, we'll come back to what the difference is between those 2 types of batteries. But one final thing I want to put in this lesson is the concept of an electron volt. All one word, electron volt. And it's abbreviated lowercase e, capital V, and EV, electron volt. And basically, it's the push required to move one electron through a potential of 1 volt. It's the push required to move one electron, or remember, whenever we say electron now, we know this means the same as elementary charge. So one electron, or one elementary charge, through a potential of 1 volt. And And if you look at your reference table, they'll actually define an electron volt this way. They'll say 1 eV is equal to 1.6 E negative 19 joules of energy. So this is a measure of energy, right? Or work. Because work and energy, remember, the same thing. They're both in joules. So an eV, 1 electron volt, is equal to a certain amount of work that you have to do to move that electron through that potential. For today, physics.